centripetal motion is what we're talking about today. The biggest thing is that we know from Newton's laws that an object in motion will remain in motion. This is the example of inertia, right? Everything wants to move in a straight line. Okay? You need something to stop it from going in a straight line if you want it to go in a circle. All right? Things do not naturally go in circles. All right? So the word centripetal we already talked about is centripetal means center seeking. Right? That's how I want you to think about it. Is that it's not centripetal, it's center. I can't spell. Center seeking. All right. So let's say you have an example here. Let's do example 1. All right. Anybody been on those on-ramps in like to get on the highway, the big like ones to get on like 90?
They're really scary. Wait, which ones?
I can't drive on those more than 25 miles an hour because my wife has a heart attack every time we do it.
Really?
So I did like at 41. She's like, oh. Anyway, what centripetal motion is your body wants to move in a straight line, right? And so when you go on that curve, the whole car is moving out of that straight line, right? And so you feel that inertia being pushed to the side. Your inertia wants you to go in a straight line. So my question to you is, what is acting as a centripetal force when you go in a big circle on that on-ramp?
Not gravity. Maybe friction. Force is normal. No, after all.
Oh, it's friction.
Friction? It's friction, right? I don't know what else. Friction?
Maddie, are you?
Well, right. First off, it has to be a force. So you're driving a blue car.
Does it matter what color?
And apparently you're in Europe.
It's a 2-lane on-ramp. Come on.
Those are good.
Yeah.
So your centripetal force keeps pushing you in. So with an on-ramp, the centripetal force. Okay. That again. On 2. Is actually going to be friction. Alright? So think about it. Your car wants to go in a straight line. But when you turn the wheels, the friction between the tires and the ground is forcing you in. That's also why when it's slick out, icy, rainy, you want to take those a little bit slower. Right? We'll explain exactly why in just a second. But when you have low friction, you could be in trouble. Alright. An example that was used in the AP conference that we did. This guy was really weird when he was talking. He was saying how to really connect with students, you need to connect with their more primal thought process. And so he always referred to everything as really gory. I know you're eating, so I'm not going to get into any details.
It doesn't bother me.
But he was saying, all right, imagine you're going down the hallway. Imagine you're 5 years old. All right, you're back to your 5 years old. And anybody have those like feety pajamas?
Yeah.
You know,
I still wear that.
Yeah.
right? And so you're running down the hallway.
For Christmas.
You're in your feety pajamas. Maybe yours has bunny ears that are flopping around, or you're hopping down, right? You're going run along there. But then he kind of changed it. He said, "But wait, you're not running just because you're 5 years old. You're running because there's a bear chasing you."
What?
All right.
That happens to me all
And not like a teddy bear, like a really mean teeth, like
Same.
everything going after you. And so he said it where you're not running as fast as you can, you're running faster than you can. And so you're going, right? All of a sudden you come to a corner in the hallway. All right? But you're wearing feety pajamas.
You're gone.
Oh, no.
Oh boy.
And you have no friction, right?
No, this is so sad.
And so, what do you do to make it around the corner?
You grab the counter. Slide. Grip.
But no, see, the counters and the walls are all covered with poisonous hooks.
Oh man.
All right?
You don't go. You don't
Yeah.
go to the corner. You keep going
What school do
straight.
you go to?
then that's the answer. Like, who put hooks on the wall? And then he's like, I did. Who do you think let the bear into the school? Anyway, so what happens is, you start pushing against the motion to get around that corner, right? That's the friction, right? You're trying to get friction to push you into the circle. So that's centripetal motion. That's having you go around the corner by having some force push towards the center of your rotation. Does that kind of make sense?
How does this make it teaching?
Anyway, so centripetal motion. He was funny. All right.
Sounds like a morbid sport.
Now, what I want to talk about is the equation for centripetal motion. All right. Everyone, write this down. FC is equal to MAC. All right. All right. So, this comes from Newton's second law, right? Centripetal force is going to be mass times centripetal acceleration. And what we're going to do here is we're going to kind of change it around. All right. There are two things I want to bring up. One is what is centripetal acceleration? Okay. So AC is equal to V squared over R. Okay. AC is equal to V squared over R.
We're really getting to like alpha and stuff.
No, we're not going to get into that today.
We got into last week, those up.
And now the centripetal acceleration always points towards the center of a circle. So if we have our circle right here, let's say we have a blue block moving in a circle. All right. Our centripetal force has to be pointing towards the middle, right? We talked about that. You need some force pushing in the middle. But also, according to Newton's second law, any time you have an unbalanced force, you're going to be accelerating. And so in this case, assuming there's no other forces acting on you, you're just moving in a circle, right? No friction, no nothing. Your unbalanced force is going to be centripetal. And so because of that, we know it's going to result in acceleration. Right? Now, I'm not going to rederive where we got v squared over r using the two vectors and all that stuff. This is given. All right, that's on your equation sheet. If you want to look back in your notes how we derived it earlier, feel free to do that. Or if you have questions, let me know. But so you have these two major equations. We can combine them now, and we then get FC is equal to mv squared over r. All right. And so something like, imagine just like a hockey puck, all right? Kind of coasting on the ice, right? And you had a string pulling that hockey puck around like a post or something in the middle of the ice. So its inertia is going to carry it in a circle, and that centripetal force is going to keep it from moving in a straight line. What happens if we cut the string holding onto the hockey puck?
It's going to go tangential.
Right, it's going to go tangential. Right, that's because our velocity vectors, now this way right here, this is our velocity, and here is our, I'll do that in purple, is our acceleration. Alright? So velocity is tangent to the circle. Acceleration is pointing inwards, and FC is also pointing inwards. Now, ladies and gentlemen, I want to make sure we're clear on this, that this is only centripetal acceleration. Do not get this mixed up with tangential acceleration or rotational acceleration. There's a lot of different accelerations involving a spinning object. All right. So this is sometimes also called rotational, centripetal, or also radial. So these are the same name for AC. All right. Why do we call it radial? Do you think?
Radius.
Yeah, because it goes along the radius. Does that kind of make sense? And so it's always pointing in the same parallel to that radius. All right. Let's do an example here.
It's going to be on a new page.
Yes.
Mr. Trump,
Hmm?
were the little black things on the bottom of the Morse code?
Of the what?
Were the bottom, are those black things blue?
Oh, these?
Yeah.
They're to reflect the signal bouncing it up and down. And so when you put your hand here, you put the pen here to reach it. Is this thing shooting lasers down? All right.
Laser.
Yeah. So let's go ahead and try out number 5. Try out number 5, all right? We have an object attached to a string as shown initially rotating in a circle on a horizontal frictionless tabletop. So this is like a bird's eye view, if you will. All right? The string is then pulled directly towards the center, and the object spirals inwards, as shown to the right. Which of the following, which arrow correctly shows the direction of the resulting acceleration of the mass at point P? So you have this thing spinning around, coasting on like a puck of ice, or a horizontal frictionless surface, and then you pull on the string. And so as you can see, it starts to spiral inward. Does that kind of make sense? Are we all out of pizza already?
No, it's all
No,
right.
no.
Oh, okay. I want to know, what does the acceleration do? All right. What one of these best describes the acceleration when you're at point P exactly? All right. So take 1 minute, talk to your neighbor, and try and get that. Ready, go.
Wait, I don't get what elaboration. It's spinning at directed towards the center. Okay. I didn't even read the problem.
Yep.
It's like, yeah.
How does it spiral inward?
Yeah, I'm having a hard time like.
Oh, okay. It's like
Yeah,
this.
I know.
Wait,
It's so bad.
It's like, so they're shortening the string, so it's spinning around, so it goes and forth to the
Yeah,
center.
it's always yeah.
It's like spinning back and
I think it's like this.
So like here, it's not really supposed to be like that. That's spinning, I'm pulling on it.
I think of that.
Oh,
it didn't go as planned.
What happened here?
So if you have a mass, so here's a quick demonstration of what I mean.
Don't throw it.
All right.
Wait.
So you have something moving in a horizontal frictionless circle. Imagine like a puck of ice. Then when you, we're going to do it like this. And then when you pull on the string, what's going to happen to the pad?
Okay.
Like that. Does that make sense?
Yep.
So now, knowing that, and again, somebody's applying force to the
top
string.
view?
So this would be bird's eye view,
Okay.
yep.
I mean, you could also do it like this, though. Yeah, but then you'd have,
Gravity.
gravity.
Oh,
darn.
So it's B then, right? C. True. C. Oh, haha.
I missed your wittiness. My class anymore.
What way is it?
I feel like I've only ever been in my class.
Yeah, just decrease it.
I've always had soap in my class.
You were my
What are you doing?
Second semester.
Katie's got her thinking hat on.
Hey Carter. Hey Carter. No one.
What?
What? Carter.
Yeah.
That was
That
for
is just
me.
wrong.
Did he pay for it?
No.
Did he?
Yeah.
Did you leave
You
like
should
money?
charge him.
Shit.
I'll go hunt him down and beat him up if you want.
He flinched though when I chased him.
What?
Oh.
All right, so who says A? Who says B?
Hey,
Who says C? Who says D?
Yeah.
B is correct.
Not like being
Tell me how.
I can do whatever I want. 'Cause I have a degree. All right.
Do you? Do you really? Yeah, do you really essentially a piece of paper
You're gonna
that
solve
you
that
that
one
you pay a
problem.
lot of money for?
I wrote my name in crayon. I don't know. Anyway, yeah, so it's B. B is correct.
Good job.
I mentioned I have a degree.
Thankfully, it's in
Okay.
physics and not technology.
What did you say?
My sheet.
All right, well, I'm going to figure this out.
You have
Hang
a
on.
degree in physics,
Oh,
not
well.
computers. Unless you have some sort of minor.
But physics and computers are so similar because neither of them ever work.
Burn. All right, so like I was saying, it's B. All right. Now take a look here, guys. Why is it B?
It wants to.
For two reasons. Number one, even if it wasn't spiraling inwards, the acceleration at point B would still be pointing in. The fact you're pulling on it doesn't change that, right? Because you're pulling on it, so the tension is also going to be in that way. And so therefore, both forces are pointing in towards the center, and so therefore your acceleration is also in towards the center. Now if you had a force, like a friction, maybe acting on it, which would then be like in this direction, then maybe I could see that, but it would then be more like C. But since there's no friction, you're just pulling straight in, it's going to be B. Does this make sense?
Yeah.
All right, let's keep moving then.
Where's mine?
There was another one. Hey, I'll deal with that one later. All right. So. Let's do a numerical example. All right. As I'm sure you're aware, it's probably not going to be too many of these, but they're mainly not. Oh well, you know what? Actually, let's do this. Let's say we have a binary star system.
I'm already confused.
Oh.
Is there a scale involved too?
Right. What?
Is there a scale involved?
Yeah. Binary star system. You put each one on a scale. Now,
Oh my.
In an elevator.
in an elevator. And it's spinning around like this. Alright. B is orbiting A. Alright. I want to know.
How?
Oh, it could be bigger, but it could weigh less.
That's true. I was like,
Very dense.
directly the bigger it is.
Actually, that depends on your point of view. Right? It depends on your reference point. Velocity is all relative. Okay.
A is just
Um,
far away.
Now, if it's orbiting here, let's say from the point of view of A, what I want to know is I want you to tell me what is the velocity. I want you to do it in terms of the force of gravity, in terms of mass. Mass. These are all known values.
Are we doing velocity V?
Yes. What am I forgetting? No, I think that's it. Yeah, radius. Yep. All right, I want you to go ahead and tell me what is the velocity of B in terms of these four known values. $2. Kayla has changed.
So you don't want numbers, you just want the...
Just variables.
You want to find the velocity of B?
Mm-hmm.
What the heck? How do we learn that?
This is how I feel about the problem.
Yeah.
Not that bad.
What? How do you do the first two?
Yeah.
I should be pepperoni food one. Alright, think about this. Assuming that it's in uniform circular motion, assuming that it's all the centripetal forces are applying to it, what is acting as our centripetal force in this case? Gravity, right? What's the equation for centripetal force? mv squared over r. And what are we trying to find? V. Can we solve for velocity?
It's force gravity divided by...
So force gravity.
Force gravity.
Radius.
Yes.
We're going to and you want to solve for
M,
B?
B, and square root M.
This is example 2, right?
I don't know
Yeah.
M of A is
M of circle A. Example 3, actually.
massive like A. I don't know how that's done. You understand?
Yeah, me either.
Alright, let's go through this.
Good idea.
We're looking for V. Now, where can we find V? Well, we know that centripetal, let me do the solution over here in red. So we know that centripetal acceleration is equal to VB over R, or sorry, V squared over R. I'm sorry, before I get ahead, did anybody have an answer they want to submit? Yeah, what do you got, Hunter?
The square root of FG times R over MB. Same.
Over MB?
I have worked with it. That's what I got too.
It's like when you write a card and you're, oh, put my name in there too. Alright.
True.
Alright, we also know that, so if we find AC, then we're good, right? And we also know that the centripetal force is equal to M times AC. Well, hey, there we go, we're like halfway there. Now take a look. In this case, the centripetal force is Fg. Alright? So when we do this, guys, we plug everything in, and we can say, alright, well that means that Fg is equal to this would be MB. VB squared over R. Alright? That makes sense? Let's say you just solve for VB squared, and you end up with square root of FGR over MB. Right?
So you can separate it like the AC or FC equals FB squared over R.
What?
Is it
Wait,
like
how do you know that
total
FC
for the whole
I know,
thing?
how do you know
can
that
split
FC
up
equals
with the
FC?
two?
That's like a multiple choice.
Is that even?
Let's say it one more time back.
So like the equation FC equals MV squared over R. It's not like of the entire system. It's just of.
Yes, in this case, yeah. Because the mass here of A doesn't impact the speed it's rotating, it only changes the force, which then kind of does impact it, but what I'm trying to get at here is if you have a rubber stopper on a string, the only thing that determines the centripetal force needed to pull it in is the mass of that stopper. That's it. Does that make sense? That was kind of a tough one. That's kind of the question you can expect. With no numbers, no nothing, and dive right in.
Why do they do that? Why do they R both sides?
Because if in AP Physics B they put only numbers in, and it's all like math crunch, and people they get to college where you actually have to understand the concepts and not any of the math. And so there was two reasons. One, some kids actually knew the physics but struggled with the math, and so then they didn't do as well on the test. And then on the other hand, some people were really good with math but didn't know any of the physics, and so then they did really well, and then when they get to college, they get crushed by actually having to understand the concept.
Doesn't it make sense that if you can do the math, you can do the physics?
Not always, because when you get to more abstract stuff, there's like in any 300 level science course, there's very little math. What math you have to do is like integrals, but it's all variables. So it's all.